a more formal empirical based approach to this problem, because that connects these multiple testing ideas with the things we've done earlier. And there's a very close connection and a very natural connection. So you can think of Q value here, this kind of procedure where it just kind of tries to, looks at the tests near one, the p-values near one, and tries to draw this horizontal line. It's kind of implicitly estimating the distribution of the p-values under the alternative as whatever's left, right? Whatever's left here is the implicit distribution of the p-values under the alternative. So it doesn't make any explicit assumptions about what that distribution might look like. It just essentially makes the assumption that the p-values are uniform under the null. And then it kind of conservatively estimates the null to be as large a portion of the p-values as it can. It subtracts that, and what's left is the alternative. And one kind of disadvantage of that procedure is that, in fact, it can be that the distribution of p-values you get that's left may be not a valid distribution of p-values. It may be an impossible distribution to obtain from any assumptions that you might make on how they were generated, at least under certain circumstances. So the empirical Bayes approach is would typically involve making an explicit assumption about the effects or the p-values under the alternative. So actually, it's easier to work with z-scores than with p-values when you're doing this. So I'm going to split. I'm going to flip to working with z-scores instead. Although the ideas are very similar. So a z-score, a null z-score will be normal 0, 1, standard normal under the null. Right. So I'm going to assume instead of, and in fact, I'm going to assume that I've seen an effect size estimate is conceptually easier to think about getting an effect size estimate and a standard error for every test. So instead of, you might get, p-values p1, pj for j tests. Instead of that, I'm going to assume that you've got a beta 1 hat and a standard error, let's call it s1 hat, for each test. Okay. Sorry, it should be 2. Okay. So I've got 2 numbers for each test instead of 1. And in fact, in many settings, that's how the p-values are computed. You first get a beta hat and a standard error, and then you turn that into a z-score or a t-score and turn that into a p-value. So in genetics applications, for example, people will, if they're interested in identifying genes that are different between, say, men and women, they'll measure the genes in a bunch of men and measure the genes in a bunch of women, and they'll get an estimate of the effect size, that is the difference in the average expression between men and women. That will be their beta j hat for gene J, and they'll get a standard error for that, which will depend on how many men and women they measured and what the variance of the expression is in each group. Okay, so think if you want a concrete way of thinking about it, that's how these beta hats and standard errors might have come. So under the null, we know that maybe that beta j hat, well, actually, maybe not even under the null. Here's a reasonable assumption. Might not always be true, but here's a reasonable starting point. We're going to assume that the beta hats are normal with some mean beta that's the true effect for that gene. So the beta j's are the things we're interested in. And we're just going to treat the standard errors as given. And that's like the difference between, if you've got small sample sizes, you might want to take account of the fact that the standard errors were estimated. But let's just assume that the standard errors are big enough that we can make this assumption. Okay, so that, you might also think of that as making that under the null, these z-scores are normal 0, 1. Right. Okay, so H0, to be explicit, is that beta j equals 0, or maybe I should say H0j and H0J1 is that beta J comes from, well, it's non-zero, but in order to do an empirical Bayes approach, we're going to have to be explicit about what that distribution might be. So let's, for the simplicity, let's assume that that's normal. So in other words, the beta J's now are a mixture, right? They're a mixture of zeros and non-zeros. And the non-zero ones are normally distributed by our assumption. Now we could change these assumptions, but let's just start. This is the simplest version, I think, of the empirical Bayes approach. Okay. So we need one more assumption because, okay, it's a mixture. We need to know that if there's a mixture, there's some proportion of them, which we don't know what proportion are null and what proportion are alternative, right? So actually, we can write that as beta J, there's some proportion pi 0 that are null, plus, and the remaining 1 minus pi 0 are normal with mean 0 and variance sigma squared. Right. So now the empirical Bayes approach has 2 parameters to estimate here, this pi 0 and this effect size. Right? And that's kind of, well, it's exactly, estimating those from the data is exactly analogous to estimating the height of this, you know, essentially this line here. You know, that in fact that line is pi 0, is estimating pi 0. What the height of that line is an estimate of the proportion that are null. Right? If all of them are null, the height will be 1. If none of them are null, the height will be 0. Yeah. So the height of this line here in Q value is an estimate of the proportion that are null. So estimating these 2 parameters, sigma squared and pi 0, is exactly analogous to estimating the height of the line, except we now have 2 parameters because this empirical Bayes approach has an explicit model for the alternative rather than just saying, I'm going to fit the null, I'm going to fit it as much as possible, and I'm just going to subtract it and call what's left the alternative. Right? And so you should know how to do this now. You can do this by empirical Bayes, right? We could just maximize the joint likelihood. So maybe I can just draw the graphical model here, maybe so we've got a pi 0 and a sigma squared, and then we've got a beta J, let's do beta 1, beta 2. These effect sizes are drawn from a distribution that depends on those parameters, and then we've got a beta J1 hat, beta 2 hat, beta J hat, and we're also, I'm treating the standard errors as known, but and actually different, so maybe I shouldn't draw. But this is just I guess because I'm treating them as known, I'm not being very careful about those, but so that these are known. I'm estimating these guys from these observations, and then we can find the posterior distribution on the betas given the estimates, which in particular will give us, we'll be able to compute what's the probability that beta J is equal to 0, or maybe not equal to 0 is maybe the more, well, if you're false discovery, it'd be the probability it's equal to 0, right? Yeah. So you could compute the probability that beta J equals 0 given beta J hat and the estimated values from the empirical Bayes procedure. And this quantity here is called the local false discovery rate. That's This is a terminology due to Efron, I believe. So it's called that. Why is it local? It's local because it applies specifically to this test, J, based on its data, J hat, beta J hat. Maybe I should also include the SJ hats here. And it's called the false discovery rate because it's the probability if we rejected that test that we would be wrong. If we called that one a discovery, if we called J a discovery, this is the probability we'd be wrong because it's a probability that it's actually null given the data. So it's a probability it would be a false discovery. So, so that's in an outline, the idea behind this, and you get the same, essentially if you applied that to, you can't apply it directly to p-values, but if you applied it to z-scores that produce this kind of histogram, then you would also get a decomposition of this histogram into a null component and an alternative component. But typically what you'll find is that the decomposition is a little different. What typically happens is it ends up drawing this line lower than Q value does. Because, I don't know, maybe I can just, in order to explain why, I think it's easier to think in z-score space instead of p-value space. So if you think about what a histogram of z-scores might look like, here's a histogram of z-scores. So of course, it's not a very good histogram of z-scores maybe, but okay. So these ones out here are the ones that are maybe quite, maybe let's say this is -2, this is +2. So some of these out here are getting quite small. Maybe there's a few out here even that are very, quotes, significant, very small z-scores. And what Q value is doing is it's essentially partitioning these z-scores into a normal component, which is the null. You know, just as in the p-value space, the uniform was the null. In p-value space, the uniform was null. In z-score space, the normal 0, 1 is null. So maybe I can, you know, kind of draw a normal 0, 1. And then what's left, once it's subtracted normal 0, 1, these bits, oh, I didn't mean to erase. Let's put them back. These bits that are left are the alternative ones, right? So just as in the p-value space, the uniform is the null and what's left is the alternative. In the z-score space, the ones in the middle are the non-significant ones, are the kind of the null, and then these ones at the tails are the alternative. And actually, if you then plot what the z-scores look like, what the implicit distribution of z-scores is under the alternative, Q value will often give you results that look like this, which basically means that there's a hole in the distribution near 0. It says you could never see a z-score of 0 under the alternative, because once it's kind of, it's subtracted the uniform p-values out, it's subtracted the null, the normal 0, 1 z-scores out, as many as it can, basically, and it leaves just the tails, and it says those, what's left are the alternative, the distribution of z-scores under the alternative, which is saying that actually, you know, you can never see a 0. This distribution is saying that none, you know, that none of our alternatives will lead to 0 z-scores, which is probably not true. You know, there are probably lots of small effects in practice that are very hard to distinguish from 0 and lead to z-scores quite near 0. Putting another way, tests don't have, you know, it's not the case that you get this very clean distinction between the null and the alternative z-scores in practice. So what the empirical Bayes approach tends to do is to say, well, you know, maybe under the alternative, we expect the z-scores to have a longer tail, and under the null, there's at normal 0, 1, but not to say that there's no z-scores near 0 under the alternative? Well, in fact, if you look at this model, implicitly, some of the alternatives will be very close to zero. In fact, under this model, the mode of the effect size under the alternative is still zero. And that's probably not unrealistic. It's probably the case usually that, that there may be many non-zero, or maybe a small number of non-zero effects, but some of them will be very close to zero and some of them will be very far from zero. Okay, so that's probably enough for you. You're probably